Back in Chapter 2, we calculated the total self-energy of a collection of charge. We said that that energy could be calculated assuming that space has an energy density equal to 1/2 epsilon naught E squared. This energy density does not account for the effects of a dielectric substance. So let's try to do that now. First, we are going to assume that we are dealing with a linear dielectric material. That is a dielectric material that has the property polarization is equal to epsilon naught times chi e times the electric field. Recall also that the definition of polarization is the net dipole moment per unit volume. With this, we can differentiate this equation and rearrange it to say that in order to change the average displacement of dipole particles, we will need to increase the electric field by a small amount, and those two relationships are given by this equation right here. Moving a charged particle with an electric field, that is doing work. And so we can say that the total work done per unit volume is equal to 1 over the volume times the total work done being the integral of force times displacement. Force is charge times electric field. And so that's how we get this. Now I'm going to use the dd of this equation, and I'm going to put that into dx here. And that gives this equation right here. And so E times dE, that is 1/2 E squared. And the rest of these are constants. So keep in mind, this is just the energy from polarization. It is not any of the energy that was initially included in this term. So that for the total energy per unit volume, we need to add this and this. So 1/2 epsilon naught E squared plus 1/2 epsilon naught chi E squared. I just did a little bit of algebra here and got this formula. Then we can remember 1 plus chi E, well, that is the relative permittivity right there. And relative permittivity times permittivity of free space becomes the absolute permittivity. Now, what we have just done is true for a relatively simple scenario, a linear dielectric that does not have any directional funkery to it. A slightly more generic term would be that the energy density is equal to 1/2 times the displacement field dot the electric field. In everything that we're going to be doing today, displacement field and electric field are in the same direction, but if there was some weirdness to it, displacement field might not be in the same direction as electric field, and so this formula would be more accurate. Now let's put this in the back of our mind. Let's consider a capacitor. Capacitor has an energy equaling 1/2 Q squared over C. We could also say it's 1/2 CV squared, but let's look at this form for a bit. Now that we are dealing with dielectrics, the capacitance can change. So I'm going to write it in this form right here, where epsilon naught is either the dielectric constant or the relative permittivity, and C naught would be the capacitance just based on geometry, i.e. the capacitance if there was no dielectric. Now, let's go back to problem 419. In 419, we looked at what would happen if you took a capacitor and partially filled it with a dielectric material. For part A, we filled it halfway vertically, and part B, we filled it halfway horizontally. Let's try to generalize the result from part B. Let's say that instead of filling it halfway, we filled it some fraction of the way. Referring to figure 430, let's say that we left that in a capacitor with plates that had dimensions L by W, we left a length X unfilled by dielectric and the remainder filled by dielectric. In that case, the total capacitance could be the sum of the two fractions of the capacitance. So this term would represent the region of the capacitor that was not filled by a dielectric material, and this term would be the portion of the capacitor that is filled with dielectric material. Doing a bit of algebra, I can ultimately come to this formula right here, that the capacitance is equal to the geometric capacitance times this, the relative permittivity minus x over L times the susceptibility. Doing it like this, we can see that as the dielectric slides in and out of our capacitor, the capacitance changes, given by this formula right here. The rate that capacitance changes is negative C naught chi over L. What this means is that as X gets bigger, i.e. as we're pulling the dielectric out of the material, the capacitance gets smaller, which matches what we've seen before. Putting a dielectric material in a capacitor should increase its capacitance, so pulling one out should decrease it. Now, when we have energy as a function of position, we can say that the force is equal to negative dE dx. Now, if I was going to write this in more vector terms, I would say it was equal to the negative gradient of energy, but since we're only dealing with one dimension, I'm going to try to keep it a bit simpler here. Using the chain rule, dE dx is equal to dE dc times dc dx. So for dE dc, we're going to go back to our formula for a capacitor. E is equal to 1/2 q squared over c, and say that, or 1/2 q squared over epsilon r c naught. Actually, no, I'm going to stick with this one. Take the derivative with respect to capacitance, and that becomes negative q squared over 2c squared. So that's this term right here. dc dx was this term right here that we just calculated. And keep in mind there are three negatives. There's the negative from this derivative, there's the negative from this derivative, and there's the negative because of how we define force. If we put it all together, we get this. Now, one more thing, because we have C naught and C, in order to simplify, I'm going to use the statement that Q equals CV and replace Q squared over C squared with just V squared. Now, you might wonder why I'm doing that. Why did I go through and use this formula for energy if I was going to replace it with V squared over C squared? That is because doing this analysis, starting off with the 1/2 CV squared formula, we would neglect to include the work done by charges moving into and out of the battery that this capacitor is potentially attached to. So what I'm doing here is I'm assuming that charge is going to be constant for the purposes of my differentiation. So I don't have to worry about that. Lastly, I could do this more generically and say that if a dielectric material is placed inside a capacitor, then the force pulling it into the capacitor has a magnitude 1/2 times V squared times this derivative, how much the capacitance changes depending on how far into the capacitor the dielectric material is. I should clarify that this force is an attractive force. Dielectric materials are pulled into a capacitor.